Okay, so let's do some physics. So I do have a homework assignment up here, and the first problem looks like this. We've got this graph that has this wave on it, right? It has a zero line here in the middle. It has these different times where it's crossing the x-axis, and you should be able to figure out those times. That's the first thing they're asking. What are the 4 times after 0 the object passes through its equilibrium position? Which are the times when it passes here? So you're going to figure out what those times are. And then it says, what's the 4 times after 0 where the object has a maximum magnitude displacement from the equilibrium? Well, that would be here, and here, and here, and here. At the peak and the trough are those times. Not hard to figure these out. But then it says, where are the 4 times after 0 where the object... oh, sorry. I'm lying to you. The first thing that you have to look at before you ever do this problem is you have to look at what is on the y-axis, which in this case is velocity in meters per second. You have to look at that first. So let's, I got to bring up my screen. You got to look at what's on the y-axis. That's velocity, and then the x-axis is time. So that actually is going to change our answers, because this is telling us how fast this thing is going, not where it is, right? And so in the case, in this case, we could say that this is like a mass on a spring going up and down. In this particular drawing, and this drawing on this first problem looks like this. So if this is a mass on a spring going up and down, and this is the velocity of that mass, then this is at the max velocity. When did we decide that the mass on the spring has a maximum velocity? At the middle point. So if this is the middle point, that's where it's going the fastest. So this is actually its midpoint, this is its midpoint, this is its midpoint, this is its midpoint. These are all midpoints, these are all equilibriums in x. In velocity, they're maximums, but in equilibriums, they're where it's going through x. So that's where it's going through its equilibrium point. So that's a little bit tricky. So for the first part, the times are when it's at its peak and trough. For the second part, it says, what are the 4 times where the object is a maximum displacement? Remember, maximum displacement happens when velocity is equal to what? This is velocity equals max. This is velocity equals 0 as it turns around, right? So this is the place where it's at max displacement, x max, right? It's when it's crossing through 0. And then it says, what are the first 4 times after 0 which the object has its maximum magnitude of acceleration? Where do we get the most acceleration? Well, also out here, because that's where it has the most force. Remember, if you stretch a spring, the more and more you stretch it, the more and more it pulls back, right? So if you have more and more force, and force equals mass times acceleration, then you will also have more and more acceleration. So the furthest out and the closest in is when it has its maximum acceleration. And where does that happen? That happens where the velocity is equal to 0 again. So maximum acceleration is right here. You can also tell that by just looking at the graph, because maximum acceleration on a velocity curve is always where the... forgot to go back to my video. So here's your maximum acceleration happens here at the crossing points at 0. And so you can also just look at the curve, because on a velocity graph, maximum acceleration happens where the slope is the steepest, and the slope is steepest here, here, as it goes through 0. And then where does it have 0 acceleration? 0 acceleration happens when it's right in the middle, which is where the velocity is at its max. So 0 acceleration here, 0 acceleration here, 0 acceleration here. And this is all because this is showing us the velocity on the y-axis, right? So we're looking at the velocity of this oscillator. So it's tricky. It's not very difficult once you figure out what it's talking about, but it is tricky for sure.
Now, in a long graph over time, do these peaks and valleys get a little bit less?
If there is damping, yes. If it's a perfect oscillator, like in our physics class, then no. So here's another example where they do a graph of an oscillator. This is a mass hung on a spring and everything else, bouncing up and down, whatever else. But in this case, they're not graphing velocity, they're graphing potential energy. Okay, so the potential energy from gravity and the potential energy of the spring. You notice that the potential energy of gravity and the potential energy of the spring look like they're kind of like opposites of each other. When the potential energy of the spring is high, potential energy of gravity is low. Well, why is that? Well, because as you're bouncing up and down on the spring, your potential energy for gravity is high when it's up here and low when it's down here. This is U gravity, high. It's high. This is U gravity, 0, down at the bottom, right? Or low. Just call it low. It's the low end of potential energy for gravity. The high end of potential energy gravity is up at the high point, whereas the spring potential energy is very different. Its potential energy up here, when you compress the spring, is at a high positive, you could think of it, or high negative, either way. It turns out that that's high. That's the maximum negative. So potential energy spring is max. They call this the max negative here. So it's got a negative potential energy at that point, and that's because it's trying to push it down. And then at the bottom, when it's all stretched out, it's trying to pull it back up, and they call that U spring as maximum positive. So on this graph here, and why does this keep switching back to? Okay, so anyway. Here's your spring. This is maximum negative for the spring, maximum positive for the spring potential energy, maximum gravitational potential energy high, and potential gravitational energy low. Now, when you look at this, you see, when you look at the graph that they show of this, which looks like that, where this is gravitational and this is spring. The top one is the spring potential energy, the bottom one's gravitational potential energy. When you have a high gravitational potential energy, right here, when this mass is very, very high, you have a maximum negative spring potential energy. It's bottoming out, right? And vice versa when the mass is low. When both of them are right in the middle, you have a potential energy that is halfway in between the maximum and the minimum. So essentially what's going on when you see this graph like this is that one potential energy is exchanging its energy for the other potential energy. The spring potential energy raises it up and gives it gravitational potential energy. And that potential energy that becomes gravitational potential energy came from the spring potential energy. So it's switching back and forth between spring potential energy changing to kinetic energy, and then that kinetic energy changes to gravitational potential energy. And then the gravitational energy goes away as it falls down again, turns back into kinetic energy, and then turns into spring potential energy at the bottom. So it's trading back and forth to these different kinds of potential energies. And they tell you the maximum gravitational potential energies. They tell you the minimum gravitational potential energies in this problem, and the maximum and minimum spring potential energies. And then you ask you something like, what is the, oh, and they also tell you how far it's moved. So they tell you the distance it moves, so you know how high it is. And they also tell you, no, that's all they tell you. And then they ask you, what is the mass? So you know how high it went. If you know how high it goes, and you know the potential energy gravitational, you can calculate the mass, right? Because gravitational potential energy is mgh. So if you know h, and we always know g, you can calculate m. Well, and you also know potential energy. So you use U equals mgh, U gravitational potential energy equals mgh, to calculate the mass. Once you know the mass, then you can plug that into the spring constant equation, which is spring potential energy, U, equals 1/2 kx squared and the x again is the maximum displacement of the spring, or the mass on the spring, then you can calculate k. Once you've got k, then you can figure out everything.
What did we do to find mass?
You use U equals mgh. I'm going to fix my...
That's the U of the spring.
So it's U of gravity, it's the potential energy due to gravity. The gravitational potential energy is equal to mg times h, and h is the maximum displacement, the maximum heights that it goes, or the maximum, it's the, and they tell you here, they say that the mass is moved 0.049 meters from equilibrium. So that means it starts here and goes up 0.049 meters, right? So that's your maximum. But they've told us that the potential energy at the top they're calling zero, and so it's the potential energy at the bottom that they're giving a negative value to. So what you do is you say if you go up 0.049 meters, then the total distance that you're going to fall is going to be 2 times 0.049 meters. So that's your h. H is 2 times the distance from equilibrium. And then you plug that into mgh with the potential energy that they give you. They tell you the potential energy gravitationally is negative 0.6243. Plug that in there, you'll get an h that'll turn out to be negative. Your h will be negative as well, so that your mass turns out positive. Then you plug in your mass. And then you use the same idea, except you don't use 2 times that distance, in this equation, the spring equation, which is 1/2 kx squared, where x is the 0.049. You only use half of it, because that's the displacement from the center. And then you calculate your k. So again, a little bit tricky, but nothing very difficult to calculate or anything. Now these kinds of problems are things that we haven't done yet. We're going to cover this in stuff today. Talking about pendulums, so we'll get back to that. We'll talk about this one too later today, because we haven't been to that yet. So this is a mass on a spring. Again, there's a car on a spring that's going to go back and forth. And it's very similar to what we've seen before. Here they're just going to have you calculate wavelengths if you know the frequency and the speed. And let's actually go to the book at this point. There's some other things that I wanted to cover really quick from what we learned last time, but we haven't done speed of waves yet. So here's one that's very simple. If you have the period, if this is number 9, if you have the period of a wave, how do you calculate the frequency? Well, it's just 1 over the period. Right? Period and frequency are inverses of each other, so if you take the period, divide 1 by the period, you'll get the frequency. And the same thing if you're trying to calculate the period and you have the frequency, you do 1 over the frequency is the period. That's number 10. Then they say if you have a planet that completes a rotation in t, they ask what the angular speed of the planet is. Well, angular speed is just frequency times 2 pi. Turns out that's just definition. That was 11. Frequency times 2 pi. And then we have some other problems where we're figuring out where things pass through the equilibrium position, like numbers 12 and 13. They give you another graph like this stuff up and down here, and it's a wave. And in the case of number 12, they're telling you the distance on the y-axis, and so you can figure out what is the maximum position from equilibrium. You can also you can write down the function as a function of time, because it's a sine curve, this one is, so you would use the sine function. Remember we learned last time sine 2 pi frequency times t. We learned about the function of a sine curve for velocity and acceleration, so that stuff you can just write down from the book. Same for number 13, except in number 13 they also want you to figure out what the period is. Well, remember the period is how long it takes to go through one wave. So you just look at the graph and you figure out how long it takes for it to go through one complete wave cycle. And then these other problems later on are things that we're going to learn about. Number 16 is one that we've already learned about, but it's just a bunch of different waves, and they want you to figure out which one has the highest frequency. You're just seeing a bunch of waves on a graph. Highest frequency has the most waves in a second. It's pretty simple and straightforward. So let's go back to the book and learn the rest of the stuff we have to learn for this chapter, which is how speed is related to frequency and wavelength in a wave. And also we want to learn about different types of waves and standing waves. Oh, and pendulums. So in 16.4 we learn about pendulums, which is a vast and complex subject, but we're only going to talk about the simplest form of a pendulum, and then we'll leave it alone. There's entire classes that are spent dealing with pendulums, physics and engineering.
What's the unit for frequency?
I'm sorry?
What's the unit for frequency?
Hertz. It's per seconds. 1 over seconds. So the very simple pendulum looks like this. It's got a mass on the end of a long string. The string has to be fairly long compared to how far it swings back and forth. Otherwise it won't behave in a simple manner. And that has to do with some mathematics that we use to simplify the equations we're going to deal with. If you look at the gravitational forces acting on this, or all the forces acting on this mass right here, you have, of course, mass times gravity pulling down, and you have tension pulling up on the string. And those two things are the only forces really on this thing. If we break this down into components of the mass here, we get this one over that's pointing this way, that is mg times the sine of theta, where theta is this angle right here. And it also happens to be this angle right here. We get two forces here actually. The point is that we get these forces here, and it turns out that angle theta becomes a very, very small angle, is a very, very small angle because of the length of the arm, the length of the pendulum string compared to the length of the movement here. And as you get a very, very small angle, the sine of an angle that is very, very small ends up being about equal to the angle itself. So if you have an angle of a very small angle, and it has to be in radians, so a very, very small angle in radians is like an angle of 0.01 radians. So if you have a 0.01 radian angle, then the sine of 0.01 radians is about 0.01. So you can get rid of the sine, which is really nice, actually. Because then your problem looks like this. Instead of mg sine theta, it's about equal to mg theta. Much, much simpler. And then you can go through this process of calculating the forces, and instead of getting something that has a sign in it, which changes all the time, you just have theta in it, and you get the force equaling something that looks like a bunch of stuff that's in here times a distance, x. And so it looks like a spring constant kind of problem, where all the stuff that's in that equation is actually m times g divided by L. That's the stuff that's in there. That's the constant stuff that's in there. And why would we care about that? We care about that because when you calculate the period of this motion, the period of this motion can be related to the period in a spring constant kind of motion, where the period is calculated with 2 times pi times the square root of m over the spring constant of a spring. So that's how you calculate the period of a spring, a mass on a spring going back and forth. And if we have something here that looks like a constant times x, and we know that the force equals negative kx for a spring, we can just call that our constant. We can say, what if we plug in our k, which is mg over L, for this, and calculate the period of a pendulum? And it turns out it works. The period of a pendulum, a simple pendulum that has a long string compared to its movement here, and that's important, that has to be that way, ends up being 2 times pi times the square root of the mass of the pendulum divided by m, the mass of the pendulum, times gravity divided by L. And that ends up equaling 2 pi, and the masses cancel out, times the square root of L over G. Now, why does that matter? You don't have to remember how that works. You just have to remember that this is true. But why does it matter? The period of the pendulum, which is how long it takes for it to swing back and forth, what does it depend on? It only depends on one thing. Well, 2 things. It depends on the length, L, of the pendulum. And it depends on the gravitational constant. So if you want to change how long it takes for a pendulum to swing back and forth, you don't change its mass. You just change how long it is. That's all that matters. Or you put it on a different planet with a different gravitational constant, right? So a clock with a pendulum on Earth swinging back and forth swings differently. It swings at a different rate than it would on the moon. It changes depending on gravity. And there's a really interesting application of this. If you go to one of the most famous pendulums in the world, which is the Big Ben clock, and if you have an opportunity to go inside and see what the bottom of the pendulum looks like in Big Ben, this is what you will see. This is the pendulum of Big Ben. There we go. This is the bottom of the pendulum arm on Big Ben. What has it got going on it? They've stacked all kinds of things on it, from coins to little widgets to blocks of things. And I just told you that it doesn't matter. The mass doesn't matter. So why would they stack things on top? Because stacking mass on top of it doesn't change Big Ben's period. But raising the mass, which would be shortening the arm, changes the length of Big Ben. So what they do is they stack mass on top of the pendulum bar, and what that effectively does is it raises the mass, and it shortens the arm of Big Ben. And if they want to lengthen the arm of Big Ben, they just take things off. And that's actually how they regulate the clock of Big Ben. That's how they regulate the time on Big Ben's clock, is by adding things to it or taking things away from it.
So an adjustment that small affects the time.
Absolutely, especially over a long period of time. So a very small adjustment, it is a very small adjustment, but they want it to be as precise as possible. And so they're constantly adjusting it to make sure that it that when the sun is right overhead, and they use astronomical instruments to measure it. Now they probably use an atomic clock to measure it, but they used to use a sextant to measure it, so that when the sun was exactly at its zenith in the sky, at the highest point in the sky, then that was noon. And if Big Ben wasn't hitting noon right at that point, they'd adjust it so that it would. And they actually have long tables, books of measurements that they've done for hundreds of years at Big Ben, so that if it's off by a certain amount at noon, they know exactly what to do to the clock, what to add to the clock or take away from the clock. And they just have boxes of things that they add and take away from the clock. And old clocks were regulated this way. Of course, if you have a grandfather clock in your house, you can also do it that way, but in that case, the mass actually slides up and down on the pendulum. They've actually designed it so that you can undo a little screw, or actually usually you just turn a little screw and it just slides it up and down on the pendulum arm. So it's a very interesting result of the mathematics that the mass doesn't matter when it comes to a simple pendulum. The mass cancels out. And that's something you need to know for the homework, because they're going to ask you to calculate the period of a clock, or the period of a pendulum. It's going to be 2 times pi times the square root of the length of the clock in meters divided by the gravitational constant, 9.8 meters per second squared. And that will calculate the period of the clock. Or they might ask you to calculate the length. So you have to rearrange this equation and calculate the length. Or they might take the clock to Mars and ask you to calculate the gravitational constant on Mars, g, which means you'd rearrange the equation and solve for g. But that is an equation you will definitely need right there. The period equals 2 pi times the square root of length over g. By far the most interesting thing that comes out of this. And that's exactly what they do in this example in this section, where they measure the acceleration of gravity on Earth. They have a simple pendulum that has a length of 75 centimeters and its period is 1.7357 seconds, calculated very precisely, measured very precisely rather. They rearrange the equation to calculate g, and they get a g of 9.8281 meters per second squared on Earth. You can't have an angle that's more than about 1/2 degree. It has to be very small, which is a very small angle in that's a very small angle in radians. It is about 0.1 or 0.01 or something. It's very small. Okay, so that's pendulums. Done with that. Then energy in a simple harmonic oscillator. Of course, we already talked about the fact that if it's a spring oscillator, then you have 1/2 kx squared. And then that's your potential energy in the spring, but you can also have kinetic energy, 1/2 mv squared. And then you can also have gravitational potential energy, which is 1/2, or which is mgh. But you can also have gravitational potential energy in a pendulum. In that case, it's 1/2, because you're replacing k with mg over L, like we did here. K is equal to mg over L. Then you replace the k in the 1/2 kx squared with mg over L. And you get an interesting equation, which is in this next section for a pendulum, which is 1/2 m times L squared omega squared for the kinetic energy. You get angular velocity instead of linear velocity, and then you get 1/2 mgl theta squared, which is the angle that it is displaced. And those two things are added together to be a constant. So that's an interesting way to look at potential energy of a pendulum. And I don't think I give you one of those. So you won't have to use that equation, but it's interesting for sure. Okay, so let's see. So many sections are in this chapter. A lot, probably. 11. Holy crap. We're in 6. Okay, so the next part that they talk about is uniform circular motion and how it relates to simple harmonic motion. And that is just going back to why the period is what it is, why I mean, it's just a review of things and a new look at the theory behind it. I'm not going to go through that section. I just want to get to the practical stuff that you guys are going to use on the homework and the exam. They talk about damped harmonic motion for a little bit in the next section, but we don't actually do any of the mathematics of damped harmonic motion. So again, I'm not going to cover it. Damped harmonic motion, though, is just where you have friction or some force involved that counteracts the restoring force and slows down the motion. I am going to talk a little bit about resonance, though, and forced oscillations. Forced oscillations, when you apply a force that increases the oscillation or that encourages the oscillation, and you do it at just the right time, you can get what is called a resonance. And the example I like to give is one that we're all used to, which is usually when you're playing some kind of game on the playground, like swinging on a swing, right? If you're swinging a little kid on a swing, when do you push them? Think about it carefully, because if you push them at the wrong time, you can hurt them, right? If they're coming towards you when you push them, you're going to push them right out of the swing, and then they fall. So that's not good. If you push them when they're at the bottom of their motion, they're going to be going as fast as they can go, either away from you or towards you. So either you're going to push them out of the swing, or you're going to push them and they're going to be gone, and you're just going to push on air, right? So you can't push them at the bottom of their motion. It's got to be at the top of their motion on either end, and it's got to be right when they're stopped and going away from you, right? So right after they've stopped and they've started going the other direction, then you give them a push. And that's how it always is when you're trying to increase an oscillation. You increase an oscillation by adding a force at just the right time that causes that oscillation to get bigger and bigger for them to swing higher and higher and higher, right? You could do it at the other end. You're just pushing on their feet and you're pushing in the opposite direction when they're going away from you on that side. But you don't want to push when they're in the middle of their motion. You want to push when they're just starting to go again, and you can give them a good push. The same thing happens with jump ropes. With jump ropes, you don't swing the jump rope when it's at the top of its motion usually. You swing it when it's just coming down from the top, and you want to use gravity and your hand to get it going again, right? So you push down as it's coming down. And it's just something we're used to. We don't think about it much. But it is this forced oscillation, adding a force into the oscillation at just the right time to create a resonance. And a resonance is when that force creates a bigger and bigger and bigger and bigger wave. That's called resonance. But when you're doing that, you have to add that force with a frequency. And that frequency happens to be at the natural frequency of that oscillator, which is the frequency that that oscillator wants to oscillate at. So I want you guys to go and look up on your computers the Tacoma Narrows Bridge and watch a video. I'll be right back. So what did you guys learn here? So that what happened was really kind of interesting. There's a persistent breeze that goes through the Tacoma Narrows, and it's not a very strong wind necessarily, but it just happened to blow through the bridge, through the structure of the bridge in such a way that it caused a vibration that was just the right frequency. It was the natural frequency of vibration for the bridge. And so over a very short time, it didn't take long, they were still building it when they discovered that it was starting to do this. That wave built and built and built, night and day, more and more and more, until it was so big that they couldn't even use the bridge. And just a few months after it was built, it collapsed because that wave got so big that it broke up the roadway, it broke up the bridge, and it collapsed into the water. So that just shows you what resonance can do. Resonance is not necessarily always a bad thing. Resonance is actually used a lot for good things. Of course, resonance is used to create music. We use resonance to speak with our voices. That's why we can make loud sound with our voices. We create a frequency that resonates within the cavity in our throat and our mouth, and it creates the sound that we can throw for a long distance. Resonances are created in many different situations that are useful, but they can also be damaging. You can break glass with a resonance, for example. If you get just the right auditory vibration frequency in glass, you can break it. So that is the idea behind resonance, is this this vibration that is just at the right frequency for just the right geometry, material, and situation, that it creates this wave that builds on itself and builds on itself, like pushing a kid on a swing at just the right time. But it has to do with a lot of things. It has to do with geometry. Where do you push the kid? At what point in their motion? Right? And if the kid's on a longer swing or a shorter swing, that matters. When you push them matters. When the vibration happens matters. At what point do you add more vibration? Because if you push them at the wrong time, you'll stop them from swinging altogether. So the where, the when, the shape, materials, the situations, length of swing, length of bridge, length, all kinds of things matter when it comes to resonance. So this is when we start talking about waves, because waves are a type of oscillation that happen again and again and again over, and they travel from one place to another. And so oftentimes they have something to do with some kind of a resonance or some kind of a vibration frequency happening somewhere and traveling somewhere else. And there are some things that we have to explain that are misconceived a lot. How many of you have been to the ocean and swam in the ocean? So when you're in the ocean and a wave passes by, what happens to you if you're just floating? And for this question to be valid, we have to talk being far out in the ocean, not right on the shore. But if you're out in the ocean, maybe 100 yards out, and a wave is coming, what happens? What happens to you? What's your motion like when the wave passes? Up and down, right? You essentially just go up over the wave and come back down, and you end up in the same place you started. The closer you get into the shore, the more you get pushed up the shore. But the further you are out, and the less friction there is with the wave on the bottom of the ocean, then the wave, all it does is lift you up and push you down, and that's it. And what that means is that the water itself is not actually moving forward and backwards. It's actually moving up and down. What's moving forward and backwards is just energy. It's just energy that is moving forward and backward. So you can actually use that energy to advantage. How do you surf on a wave and move forward? Does the wave just push you forward? Is that how surfing works? No, surfing works is you get up on top of the wave and then you lean over and tip down the front edge of the wave so that gravity is taking you forward. You actually use gravity, and you go down the front slope of the wave, down that front crest of the wave, and you use gravity to propel yourself forward. And if you're good enough at it, you can go down and then go back up and then go down, and you can ride this thing for a long time. I mean, minutes at a time. You can go up and down using gravity and potential energy and kinetic energy and potential energy and kinetic energy to go up and down, but you're not actually using the wave itself. You're using gravity. The wave creates this crest, this hill, that you can slide up and down. You're not actually riding the wave, you're riding gravity. So it's energy that you're using to surf. It's not actually the wave itself you're using to surf. The wave itself is just up and down. This is what we call a transverse wave, which means it's waving in 90 degrees. Transverse means across the movement of. So when you the wave is waving up and down, but the energy is traveling forward. So the energy of a water wave on the ocean is traveling forward, but the water is actually moving up and down. Transverse wave. But there's another kind of wave that we call a compression wave, or a longitudinal wave, and that's this kind of a wave, where you have a medium, a material of some kind, and it's waving like this. So it's not waving like this is a water wave. This is a transverse wave. We're waving back and forth. But you can also have a wave that starts in the same direction. It waves in the same direction that it moves. Right? So it's like you're pushing against something, and then it pushes against the next thing, and then it pushes against the next thing. And the propagation of that pushing energy is the wave, and the waviness of it is a compression and then a rarefaction, or compression and expansion of a material. And that is the case with sound. When I make sound, what happens is I compress air, usually. I can do it inside of a table too, but when I make sound in the room like this, I can compress the air. I can clap, and I can compress the air. Then as it compresses, it creates another compression next to it, and then it expands and creates another compression next to that, and then it expands and creates another compression. And that compression, expansion creates a wave that's moving outward from my clap. And then you hear it as those compressions hit your ear. Right? So that's what we call a compression wave or a longitudinal wave. And that is shown in the book as well, with a slinky with some sound waves, compression waves versus transverse waves here. But then the other thing that we learn here in this section is how do you calculate the speed that the energy of the wave travels with? If this energy is traveling forward with the wave, in a compression wave or in a transverse wave, how do we calculate that speed? Well, we already have two things that might give us a clue to that. And that is the frequency, which is measured frequency, which is the number of waves per second, which is given in hertz, which is per second, so 1 over seconds. And then we have the wavelength, which is how long the wave is, and that's measured in meters. And speed, or velocity of the wave, is meters per second, right? So what if we just multiply the speed and the wavelength? The wavelength being how long the wave is in space, from one point of the wave to the next point of the wave that's the same. So like from peak to peak or trough to trough, for example. Then if you take that wavelength and multiply by the frequency, you're going to get something in meters per second. And it turns out that is the velocity of the wave. So the velocity of a wave, VW, is just equal to frequency times wavelength. We use the lambda for wavelength. Frequency times wavelength is the speed of the wave. So if you know its frequency, you know its wavelength, you're good to go. So they have an example where we calculate the wave velocity of an ocean wave, where the crests are 10 meters apart, and the time for a seagull to bob up and down and back up again, which would be the period, right, is 5 seconds. The frequency is 1 over 5 seconds, So you get 10 meters divided by 5 seconds, which is 2 meters per second. Remember, the period equals 1 over frequency. So you can also say that the velocity of a wave is equal to the frequency, is equal to the wavelength divided by the period. But what would be well, let's then you get things like the speed of sound. What would the speed of a sound wave be? Well, you know, the speed of sound is a bit different. The middle C, for example, or let's say A, the note A just above middle C is 440 hertz. So there's your frequency. The wavelength is, I want to say it's a little bit less than a meter, but not much. And so if you do a meter and you divide by the 400, or you multiply by the 440 hertz, you get a speed of about 440 meters per second. That's about 400 meters per second, which is about the speed of sound in air. If you do the same thing for light, I can't really, well, I can. So the frequency of microwaves is in the gigahertz range, in the billions of hertz, so you got a billion for your frequency. And the wavelength for a microwave is in centimeters, so that's 0.02 or 0.01. So in centimeters, but it's actually for a gigahertz, it's about a 10 centimeter wavelength. So it's about 0.1. So you take a billion times 0.1, and you get 100 million meters per second for light. And that's about right. The speed of light is about 300 million meters per second, actually. But you get the idea. You can actually calculate the speed of a wave by, if you know its frequency and its wavelength. Now, how much faster is light than sound? This is something not many people are aware of. I love watching the superhero movies. My boys love watching the movies because they love superhero movies. I love watching them because I love to point out the bad signs. So in the Flash movie, the Flash TV show and movie, for example, you have the Flash who's breaking Mach 2, and then breaking Mach 3 and Mach 4 and Mach 5, and then all of a sudden breaking the speed of light. So Mach 1 is the speed of sound, Mach 2 is twice the speed of sound, Mach 10 is 10 times the speed of sound, which is 4,000 meters per second, which is still 1,000 times lower than the speed of sound. 10 times the speed of sound, or times the speed of light, is 10 times the speed of sound is 1,000 times slower than the speed of light. The speed of sound itself is 1,000,000 times slower than the speed of light. So it's actually 10 times more. So if you go 10 Mach 10, which has never been reached by humankind in any situation, if you're going 4,000, let's see, that would be 4,000 meters per second. I guess we've gone 4,000 meters per second on the way to the moon, I think they were going almost that fast. But anyway, 4,000 meters per second. You're going that fast, and you're still 10,000 times slower than the speed of light. The speed of light is so much faster than sound, it's just ridiculous. And not only that, once you start going that fast, things really start to get weird. Because if you're going as fast as the speed of light, imagine this. You do something, and somebody that's in front of you sees you do it. But you arrive at their position at the same time they see you do that. So when you leave, going the speed of light, you arrive at the same time they see you leave. Because the light that is traveling to their eyes when they see you leave is traveling at the same speed as you are. So you leave at the same time you arrive, according to them. Things start to get weird at the speed of In other words, it took you absolutely no time to travel from one point to another, according to the person who was watching you travel closely. It's kind of weird. Time starts to mean different things at the speed of light. But that was the whole point of the TV show, is that supposedly, the Flash can travel faster than the speed of light and then travel back in time. Which again is goofy, because if you travel back in time, then you leave before you arrived before you left. So what if you forgot to leave? Would you still arrive? Or so traveling faster than the speed of light creates paradoxes, paradoxi, creates these mysterious things that can't be explained. And since they've never been ever observed, if anybody had ever traveled faster than the speed of light, then we would have observed these strange things at some point. And no one has ever observed those things, so the only thing we conclude is that you can't travel faster than the speed of light. So anyway, I like talking with my boys about those things, and they just tell me to shut up and enjoy the show. I have a hard time with that. Okay, so in the last two sections here, we're going to learn about some important things that you'll need to know for your homework. Well, particularly section 10. And that is superposition and interference. What does it mean? It's simple and complex at the same time. We're going to try to stick with the simple. But superposition really means exactly what it sounds like it means. Super means to put over something. So when people say, I'm super happy, that means you're over happy, right? In our case, we're literally and physically going to put something over something else. Superposition means we're going to position something over another thing. And we're particularly talking about waves. So we have a wave. Here's our wave. And I'm going to put another wave over that wave. I'm going to put this wave over it. I'm just going to put it right on top of it, just like this. That's superposition. And if these two waves are the same kind of wave, if they're both water waves, then they will combine into a new wave, which is what we call interference. They will interfere with each other. So superposition and interference. The interference wave, or the wave that is the result of these two waves added together, will literally just be the addition of these two waves. Superposition and interference is about addition. So I take this wave, if I say that this is my 0 point coming through here, and this is positive, this is negative, then I get 0 plus 0 starting right here, which on my new wave is just going to be 0. But here I have, let's say that this is 1. I have 1 plus 1, so instead of being 1, it's going to be 2 at that point. So it's going to make it bigger, right? But right here I have 0 plus 2, so it's going to be 2 here. And then it's going to be, so the overall wave, if I keep doing this, I'm going to get this thing going on. Wherever it's a peak, I'm going to get a little bit more wave. Wherever it's a trough, I'm going to get a little bit less wave. And my new wave is going to look like this. And it's going to go down. Actually, it's going to come down because this wave's coming down. So it's going to come down. And then it's going to go down here. And the new wave is going to look like that. Can you see how that purple wave is an addition of the two waves? It's the sum of the two waves. This one got added to this one.
Is that how modulation works?
It is how modulation works. Well, it depends if it's amplitude modulation or frequency modulation. This is amplitude modulation. So this is how AM radio works. On AM radio, they have a carrier wave, which is the frequency of the radio station. And then they have the wave of the sound that they're transmitting. This is the sound wave that they're transmitting. And then this is what the overall wave looks like. And that's what you use to make the sound on your radio on the other end. That's called amplitude modulation. So they're modulating the amplitude a little bit. So it's getting bigger in some places and smaller in other places. And it carries the sound that way. Frequency modulation, they actually change the sidebands of the frequency. They vibrate those back and forth. They change the wave this way. The frequency change. So that is modulation. Here's another very simple one that you'll see in your homework. Here I have a wave that looks like this. This is also a wave. It's called a square wave for obvious reasons. So here's a wave, and then here's another wave. Let's do this. This one's going to look like this. And then they're going to ask you to add them together. So you're going to have to add these waves together. How would you do it? Well, let's say that this is at -1, and this is at +1, and this is at +2, and this is at -2. You just add them. At this point in time, you have 0 plus 0, so that's 0. At this point in time, you have 2 plus -1, which is +1. And then at this point, all the way from here to there, you have that. And then from here forward, you have 1 plus 2, which is 3. So then you go up to 3, up here, and so on and so forth, right? So you're just adding superposition and interference. Now, what's interesting about this? Well, a lot of things are interesting about this, but one thing that's interesting is you can do things like double your pleasure, right? Here you have two waves. One like that. And you have another one that you're going to interfere with it right on top of it like this. What happens to the resultant wave? It gets bigger everywhere. The resulting wave is a wave that is essentially this, right? It gets twice as big everywhere, right? You add up peak and peak, you add up trough and trough, you add up peak and peak. This is what we call constructive interference. Constructive interference builds the wave bigger. This is complete constructive interference. It has nothing but constructive interference. It just makes it bigger everywhere. But you can also do destructive interference. So here's our first wave. Here's our second wave. What's going to happen with that? This and this is going to cancel this, and this is going to cancel this, and this is going to cancel this. You're going to get a wave that looks like, boop. It's going to be a flat line. Can you do that with waves? You can do it with any wave. You can do it with water waves. You can have two water waves that will interfere this way and make a flat region. Make a nice, even region. Okay? But you can do it with sound waves. You can do, if you, have any of you ever connected a speaker system before? No? So if you've ever connected a speaker system before and followed the instructions, they always tell you, make sure that you connect the red wires to the red things and the black wires to the black things. Always. Why? Because then the speakers are going at the same, they have the same, what we call phase, which means they're pushing out at the same time and pulling in at the same time. That means the waves are coming out together, and most of the time they're adding together to make constructive interference, so that you get a nice, full, loud sound everywhere. However, if you switch the wires on one so that when this one's pushing, this one's pulling, the waves are going to be opposite like this. And you will have lots of places in your room, where the speakers are, where you won't have hardly any sound at all, or maybe even zero. You can actually cancel sound completely out. That's how active noise cancellation works with active noise cancellation headphones. With active noise cancellation headphones, there's a microphone outside the headphones that records the sound outside the headphones, and it's looking for certain frequencies that are easy to hear through headphones, like high-pitched frequencies. And then it creates those frequencies out of phase inside the headphones so that it cancels out those sounds that are coming through your headphones. That's it. If you get in a John Deere tractor these days, a nice new John Deere tractor, you shut the door and you turn on the tractor, you will not hear the whine from the turbine in the diesel engine. The diesel engine, those things have an incredibly loud, high-pitched turbine because they're extremely powerful. All tractors have it. But if you get into a Caterpillar tractor, Case tractor, John Deere tractor, all the high-end tractors, New Holland, they all have speakers on the inside that are surround sound speakers, and they're not there just for entertainment. They do use them for entertainment, but that's not the reason that they're there. The reason that they put in that surround sound is so they can cancel out that sound and protect the hearing of the operator. Because if you sit in that tractor, if you're an old timer and you've been sitting in those tractors for 20 or 30 years, you are deaf. How many of you know a farmer that's running those tractors? They're all deaf, especially that high frequency. Because they've been listening to those stupid high whining turbines forever in their lives, you know, and they're just, that's the reason they're deaf. So my father's deaf for a different reason, but he had that same frequency thing from shooting guns. If you shoot guns without ear protection for a long time, you get that high frequency ping that deadens your ear. But they actually developed that at the university I went to, Brigham Young University. They developed that system for Caterpillar, and everybody else kind of took it from there. But yeah, noise cancellation headphones can be quite expensive for active noise cancellation because they have all these extra electronics in it. Yeah, they're pricey for sure. So this is what we call interference and superposition, constructive interference. There's another interesting thing with this, and that is when you have two sounds very, very close together. Let's listen to this. So when instruments are tuning, they listen to a note and then they play a note, and often people just think, oh, they're just trying to match that note. Well, that's true, but they're also listening for a certain type of sound. So here are two sounds that are very close to each other. They're the same frequency almost, but not quite. I can't turn my volume up. Can you hear that? When you have two frequencies that are very close together but not quite right, you get a difference in frequencies because of the interference. And this is what's happening. One frequency of sound has a wavelength like this maybe. The other one is either slightly longer or slightly shorter. We'll make it slightly shorter. It's kind of like this. And the overall wave, when you do the interference pattern, looks like a frequency that is similar to these, but gets louder and then softer, and then louder and then softer, and then louder and then softer. Because here they add together, but here they start to, they have a peak that's closer to a trough, so it doesn't give you as big a peak. And then over here it gets louder again, and then over here you have a peak that's kind of off center again, so it gets softer again. So you get a louder, softer, louder, softer, louder, softer, and that frequency is actually, you can calculate the frequency of that loud, soft by just taking the difference of the frequencies. And the closer your two frequencies are together, the closer those two notes are together, the faster that beat frequency gets, and you won't hear it anymore. But if you're off by quite a bit, then you can really hear this, and then it sounds terrible in the music. So musicians listen for that beat frequency, and if it's a pretty significant one, they adjust their instruments until it goes away, until they can't hear it anymore. So that is beat frequency. And now we're on to the next section, last section, which is energy in waves, the intensity of a wave. So intensity we've talked about before. Have we? Yeah, we have. Intensity is power divided by area, which is power is energy divided by time. So intensity ends up being energy divided by time divided by area. And then if you wanted to calculate the energy, you would have intensity times area times time. But essentially, this is the equation that we're dealing with. Intensity equals power over area, which equals energy over time over area, right? Which also equals energy over time times area, like that. But what we're talking about when we talk about this is the intensity of sound, for example. If you want to calculate the intensity of sound, then you need to know the power of that sound, which means you need to know the energy of that sound divided by the time that it's taking that sound to be delivered to the area divided by that area. So a good example of what this equation means is if I'm talking to you guys like this at this volume, which is a fairly high volume, and I know I'm speaking loud because when I go and talk to people in the hallways, my wife says, you can talk quiet in the hallways because everybody can hear you down both ends of the hall. But I'm used to speaking in a classroom, projecting my voice. So I speak very loud. If I walked up to you and spoke with this amount of energy directly into your ear, all of that energy and power would go into a very small area. And you would get a lot of energy over time into a small area, which would mean a high intensity, right? But you don't get that when I'm talking over here. Why not? What's happening to my voice since I'm talking here? It's spreading out, right? And so some of that energy is hitting the screen over there, some of it's going out the door so that they have to listen to it out there, unfortunately. Some of it's hitting the whiteboard, some of it's hitting the ceiling, some of it's hitting the floor, and just a small amount of that energy gets to your ear. Same area that's hitting your ear is the same area, but the amount of energy is going way down, right? And if I took all of the energy that I spoke with in an entire classroom and compressed it all into 1 second and then put spoken into your ear, no matter where it was in the room, it would hurt. But since I spread it out over 2 hours, it's not so bad, right? So that's kind of what that equation is conveying to us here. And I don't think I gave you any questions about intensity of sound either, so you shouldn't have to deal with it in the homework. But that is all of the chapter on oscillatory motion and waves. And what we're going to do in chapter 17, which we'll start on Thursday. We'll do an experiment with it tomorrow, but we'll do the bookwork on Thursday and the homework on Thursday. It's essentially going to be everything we learned here, just applied specifically to sound. We're just going to do some very specific examples in the sound and hearing. So it's not nearly as intense as this chapter. I don't even think this chapter is that intense. So let's go back now and take a look at the homework and see if we can now clarify some of these things that we didn't know about yet in the homework. For example, on number 3, we have Megan the astronaut visits planet X, does a low-tech experiment to demonstrate physics, making a pendulum that has an oscillation of exactly 3 seconds. How long should the pendulum be? You should know how to do that now, right? Because you have an equation that tells you the period is related to the length of the pendulum, right? That equation was something like period equals mass times square root of L over G or something like that, right? So you have an equation for that and you're pretty much done. I mean, this whole problem is just that equation. So it's not a problem. Well, he also does a spring and a mass, I guess. So you also have to do the spring and the mass problem. But it's the same kind of idea. If we go to question 4, a string is stretched taut and tied between 2 fixed ends. It's made to vibrate and the frequency is adjusted until you form some waves. And so you have some waves on this string now, and you can actually measure the wavelength. You can figure out the wavelength, and they tell you the frequency. And then they ask you for the velocity. Well, velocity is just wavelength times frequency. So you know that already. So you can calculate that. And they also ask you for the period, and you can calculate the period because it's 1 over the frequency. Number 5 is just a car on a spring going back and forth, and it's just the exchange between potential energy and kinetic energy. The potential energy of the spring, when it's compressed or stretched to its maximum, becomes the kinetic energy of the car in the middle. So you can calculate the kinetic energy of the car in the middle, which means you can calculate the velocity of the car in the middle. It becomes really quite simple. Wavelengths of different notes in the musical scale. They give you the frequency, they give you the speed of sound, and you have to calculate the wavelength. Again, speed is equal to frequency times wavelength. It's very simple. It's the same equation again. That's number 6. Number 7, 6 times per second is the water dripping. The waves are certain meters apart. That means that tells you the wavelength. So you know the wavelength and period. Wavelength divided by period is velocity, right, of the wave. This is the only one that you have to do a little bit of thinking with, and not just plugging into an equation, which is number 8. Donald hears thunder 7 seconds after a flash of lightning. Okay? How much faster is lightning, the speed of a lightning wave, rather than the speed of a thunder wave, which is a sound wave? It's 1,000,000 times faster, right? So you can consider the time that passes when you see lightning, that the time from the lightning striking to when you actually see it, you can consider that time to be 0. It's so little time between when lightning actually strikes and when you actually see it. You can consider that 0. So you can just start your time right then. And so when you see the lightning, you start counting, and you count to 7, and then you hear the thunder. So you know that the thunder took 7 seconds to get to you, and you know how fast it's going, so you can calculate how far it went, right? Turns out to be about a mile at 7 seconds. It's about, it's about a mile, a little bit more than a mile. It's about 5 or 6 seconds for a mile for thunder. And then they do an echo across a canyon, so you can figure out the width of a canyon if you know the speed of sound. It's not very hard. Frequency of a wave with a period of 0.0047. You already know that. We already talked about that. Frequency is the inverse of period. So the only one that I'm going to remind you of, I mentioned it before, is the angular frequency. When you're going around in a circle, the angular velocity of omega, remember that angular velocity thing, is equal to 2 pi times the frequency. So however many times you go around per second is your frequency, the angular velocity, or the angular, which is also called the angular frequency, omega is the angular velocity and the angular frequency, is 2 times pi times the frequency. So that's an equation you need to know if you're doing rotation and stuff. 12, you just go back to the beginning where we talked about the functions. 13, we already talked about. So 14, we have 14 is a question you won't be able to answer until you do the lab tomorrow. So save number 14 for when you do the lab. When you do the lab, you're going to learn about how the speed of a wave traveling through a stream is affected by the weight of the stream and by the tension of the stream. So you'll learn that in the lab tomorrow. So save number 14 for tomorrow, for figuring out till after tomorrow. Number 15 is interesting. And I'm going to let you guys figure it out. But number 15 shows you the directions of the movement of the string. It gives up and down arrows for different points on the string, and you have to figure out which way the wave is moving. And it's a tough question. So think about it carefully. It's probably going to be different than you imagine. But think about it carefully. 16 is easy. 17 is red light emitted by a laser has a wavelength of a certain thing, and then they ask for the frequency of the light, but you have to know the speed of light. The speed of light, C, is 2.99 times 10 to the 8 meters per second. So 300 million meters per second. And I had not mentioned this, but we'll mention now. There is only one kind of wave. Well, that's not entirely true. There are only certain. There are very few ways that can travel without having a medium. In other words, they can travel through pure vacuum. Here's just empty space. Very few waves can do that. Can any of you tell me which waves can do that? Electromagnetic waves can travel through empty space, right? So that's light. Light, microwaves, X-rays, infrared, those are all light waves, electromagnetic waves. Radio waves, they can all travel through empty space. And gravity waves, now that we've discovered them, are another way that we can do that. So gravity waves and electromagnetic waves are two kinds of waves that can travel through empty space. There are other ones as well, but we won't talk about them till next semester.
So are all electromagnetic waves one light?
To a physicist, yes. To almost anybody else, no. Even most scientists consider light to be the light waves that we can see, or the electromagnetic waves that we can see. Physicists call them all light, right? Because they all travel at the same speed, they're all the same thing. And a big reason for that is because physicists deal with more waves than most other scientists. Most other scientists deal with very few types of waves. So an example of this is the matter wave. A matter wave is a wave that atomic physicists talk about and particle physicists talk about quite a bit. And other people know about, but they don't really get it. They don't really understand what a matter wave is. I've heard chemists explain matter waves as really short wavelength light waves, which is not what they are. It has nothing to do with light waves at all. And there's nothing like that. A matter wave is so different from a light wave, so different from every other wave, that it's just ridiculous to explain them in any way related to physical waves or energy waves, because they're nothing like that. All right. So it's kind of crazy to think of them that way, and physicists feel this way, that if they're the same kind of wave, they should just be all called the same kind of thing, because if you don't, you start to confuse other kinds of waves with them. So yeah, to a physicist, all light waves are just light waves, all electromagnetic waves are light waves.
I heard it described once as like an antenna that's sending out electromagnetic waves at frequency, radio antennas.
Yeah, and that's a really good way to make electromagnetic waves. Is you have an antenna, then you drive the electrons up and down the antenna, and accelerating electrons create electromagnetic waves. So
the way this person described it was that essentially the receiver is just detecting, like if you had a way to shift the visible spectrum of light all the way to the point where it was matching that electromagnetic waves, you could see those electromagnetic waves light.
yeah, I mean that's so what happens on the other end is you have another antenna and these electromagnetic waves encounter the electrons in that antenna and drive them up and down. And that's the signal that you amplify and you listen to or you watch on TV or whatever. Yeah, so and those waves are, but again, people confuse those waves, radio waves, with sound waves. They say, well, you're detecting sound waves. You're not detecting sound waves at all, you're detecting light waves. You just happen to have a carrier frequency for an amplitude or a frequency modulation that is at the same frequency as sound waves, and we use that frequency of electromagnetic radiation to make a wave of electrons inside some electronics which drives a speaker and then creates sound at that same frequency. So it's a conversion from one wave to another wave to another wave when you're doing radios, for example.
Radios work.
Yeah, so it's very confusing when you talk about waves with people because they want to try to make one wave, correlate with another wave when there's no correlation. So here they do some more frequency, wavelength combination, things like this. Mechanical waves traveling through a medium, different wavelengths, different frequencies, again. There's one last thing the last question asks you about where you can touch a wave without disturbing it. So waves have this oscillatory motion, of course, and right here we call these places right here the equilibrium points when we're talking about standing waves, but we also call them nodes. So this node is a place where if this is describing the movement of the material is zero at this point, at the node. So it's not moving, it's not waving. So if you come along and you see a string that's vibrating, you'll see a point where you'll see these troughs and peaks that are going back and forth in this one point that's just sitting there. And if you went and touched the wave there, you wouldn't affect it. But if you touch it where it's moving a lot, the whole wave will get messed up. And that's what they're talking about. You can touch it at the node. You cannot touch it at the antinode where it's moving along.
And that's what they mean when they talk about ascending node or descending node.
So a descending, ascending node is where if the wave is moving this way, an ascending node is this one where the wave is coming up to it. And this is where it's coming down to it. That's a descending node. But the nodes are just places where they're not moving. So, are you guys going to work on homework today, or do you want to be done for the day, or what do you want to do?
Either way, we're going to be working on homework. It's just whether to do it here.
Okay. Well, you're welcome to work here at 11 o'clock, which is my office hour time. I have a meeting in my office with somebody. So I can help you guys up until 11. But at 11, I will be busy during my office hour in my office. Crazy thing. What time what? So what kind of waves require a medium? What kind of waves don't require a medium? Electromagnetic, right? Mechanical waves are waves that are moving material, moving things. So that thing that's moving is your medium, right? So it definitely requires mediums. I have to get a drink of water.
Well, it's funny, I got 22 hours of vacation that's only burned, and I had to burn about 16 hours. That's their, basically, they made it work the holidays and it was not long.
You're taking next semester, right?
Physics. No, I'm going to ask for this semester. I got a lot of catch up I need to schedule with you.
You're only taking one semester, right? Same with Kyle. Well, is Kyle just one semester? Milo's just not next semester.
That sucks. Is he still going to be working here, or is he going back to wherever?
He'll be in Lincoln. He'll be taking some classes, some graduate courses. He'll be back in December. So this class is going to be cut in half next semester.
stud, catch-up games work a little better. All the chaos. Yeah, I need to schedule, see if I can do some late submissions on various tests that I spaced, especially in trade. I don't know how I can actually accomplish that.
Well,
Does, when a wave goes through, it just says how can the particles in a medium move as the wave passes through? They go up and down.
in a transverse wave, they go up and down, so that's the wave that's like this. But in a compression wave, the wave moves this way, and they move back and forth, forward and backward. But what's the question again?
How can the particles in a medium move as a wave passes through?
So to propagate forward means they actually just move forward with the wave. But these ones, when you have a compression wave, they move back and forth.
So that the options are left and right, does not move, vibrates up and down, or propagates.
I would say left and right, up and down.
Just doing what the schedule. Okay, so I've got here to here. If I call in today, I don't think they have anything for me. It gives me all afternoon to work on stuff. I figure out which things I really want. Sorry.
Sorry.
I tend to have to reason things out loud or it doesn't stick in my brain.
See ya.
Which part can you touch it? It's on
That's the node we call it.
the amplitude of the wave at this point is, it's not moving.
That's right, so it's low amplitude.
Wavelength is frequency over
Wavelength is related to both velocity and frequency. So velocity equals frequency times wavelength. Okay. So I'm going to stop.